All right, so from these images of grains on an optical microscope, we can actually use that to determine the grain size of a polycrystalline material. So this is important information because we'll see that the grain size in later chapter has a huge influence on its multiple properties. All right, so let's talk about what we mean by this grain size and how we determine it. So the images that we collect from the optical microscope, because they're on the micro scale, we call them micrographs, and it's just showing you the microstructure, so what the grains are, etc. And so this is just a sketch of a grain structure with the black lines representing grain boundaries and the white regions, the interior of a given grain. And the first thing to keep in mind is that this is our real material, our polycrystalline material. These grains are three-dimensional, right? But what we're doing is we're looking at that three-dimensional object, the grain, but we're slicing it. We're taking cross sections. And so these are two-dimensional slices of the grain. So that's something that we have to keep in mind. And so often if we really want to represent the structure, we have to take multiple slices in order to get, or different angles in order to represent the entire structure. And so what we're trying to do here with the grain size is to approximate the radius or diameter of the material, but again, we're doing slices. So it's basically like trying to estimate the radius or diameter of the Earth by making random slices. So we have to be careful with the assumptions that we make. And so if we really want to know, we would have to take slices at different angles of the material to make sure that we have a full representation of what that material is. All right, so let's look at how we actually determine this equivalent radius or diameter. And so what we do is we determine the number of intercepts that the boundary has with a line that's drawn on our material. So basically, we would print out or do this on the screen. We would draw a line of known length, and this length, since it's printed out on this page, is going to be, have units of millimeters or centimeters. So we know the length of this line in our real space, what we're looking at, and that's millimeters. And we want to try to put that line randomly so that we don't put any sort of bias into the measurement from wanting to make, for example, our lives easier and put it on a certain line. So we want to randomly orientate this line. And then what we do is we count up the number of intercepts on that line. So in this case, if I look at line 7, what we're calling line 7 here, if we count up all the intercepts, we see one here, 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 and here. So in fact, on line 7, there are 7 boundaries. And so we count that number and we know the length of the line. The next thing we need to know is, because the length of our line is from our sort of printed out or magnified image, we need to know what the magnification of the image is. And so we need to determine the magnification of that micrograph. And what we do is we use the scale bar down at the bottom usually. And so what we do is we measure the length of the scale bar in our printed out version or on the screen, right? So that's going to typically have we want that to have the same units as our line measurements. And then we convert that length, because we also know that the length of that line because we're magnifying that image, this is the length that it actually is in realistically, right? And so in this case, that line represents 100 microns or micrometers. And so what we do is we calculate the magnification by the ratio of the measured length, so that's the millimeters, over the number appearing in the scale bar. And what we want to do is, since it's a ratio and we don't have units on that, we need to make sure that they have the same unit. So microns and millimeters, one of those has to get converted to calculate the magnification. So after we've done that, what we're going to do is we're going to determine what we call the mean intercept length. And this equation is given to us in our textbook, Callister. So the mean intercept length is this script L with a bar over it. That implies a mean or average. And then we calculate this by the length of the line, or lines if we take multiple of them. So that's the length that you measured of your line. And then we count the intercepts, capital P, and then the magnification that we just calculated. So all of those go into this mean intercept length. So we count up the intercepts, add the lengths of the line or lines, and then this calculates the mean intercept length. And what we do from there is that the ASTM, which is an organization that makes standards for materials, has come up with a grain size, what we call a grain size number. And so this number is representative of how large or small the material is. And so to calculate this grain size number G, we plug it into this expression that really just is a function of the mean the mean intercept length. And so this function is when your units are in millimeters. So the specific numbers here are for when you have millimeter units. So this is a dimensionless number, and it gives us a measure of how large the materials are. And so what you can do is just as you're going through examples, or if you just want to plug in some numbers, what you want to think about is two materials. So if you have a grain size number of 1 and you have another material with a grain size number of 2, think about which one has the larger grain size, radii diameter, and which one has the smaller. So I'll leave that for you to think about. You can plug in some numbers, or you can see it in the examples that we do, but just think about what the grain size number is actually telling you about the grain size.